You are given a string and you have to partition it into the maximum number of consecutive segments such that each partition is a prefix of the original string. In the example that you see on this screen, you can see that I have partitioned it into the first segment as AB, which is already a prefix of the string. Second segment as ABA, which is also a prefix of the string, this prefix. Third segment is A, which is of course a prefix of the original string. Fourth segment is ABA, which we have already discussed is a prefix of the original string. Fifth segment is AB. You can see that that is also a prefix of the original string. And the last segment is ABAB, which is also a prefix of the original string. So your goal is to find out that given a particular string of length n, what is the maximum number of valid partitions that you can do such that the each partition is still a prefix of the original string. So I hope the problem statement is clear. I'll repeat it once again. You are given a string, you have to make some cuts over here such that after making the cuts, each subarray that remains, each segment that remains should be a prefix of the original string. And you have to maximize the number of segments that gets created. In this example, you can see that the total number of segments that you can create is 6. You cannot create more than that. In this video, we will talk about 6 different solutions to the same problem, and we'll optimize this from n to the power 4 to n to the power 3. Then we'll optimize it further to 2 different variations of O of n square algorithm. One of them is lesser known. And from this n square optimization, we'll optimize it even further to n log n, which is a standard technique, and another n log n solution, which is a novelty. And if you are interested, there is actually a final optimization that you can do to reduce the time complexity down to O of n. We will not dive deep into the details of the O of n solution in this video, but I will give you some hints and insights on how to approach the O of n version of this problem by yourself. It's not that difficult if you are able to follow all the other sections correctly. So this is going to be a long video, and I do not expect you to watch the entire video in one go. Feel free to take breaks and come back to the video as you see fit. And if you are not at the level to actually comprehend the solutions that I talk about in the n log n section, that's fine as well. If you want to skip after just solving the n to the power 4 version, you can do that. If you think that only n square will benefit you, you can skip the video after watching the n square section. But no matter what skill level you are at, there will be some section of the video that you will definitely find helpful. So let's start with the video. Even before you come up with any strategy, you have to think about the simplest possible operation that you can do. That is, if you have this string, you have to partition it into the maximum number of segments. But where do you start? You don't even have the first idea to approach this problem. So one common technique in such problem is to start with just one segment. Now that segment can either be from the left hand side, that is the first segment, we focus our entire attention to the first segment, or we focus our entire attention to the last segment. So in this problem, let's focus our attention to the last segment, and during the later parts of the video, I'll tell you why I chose the last segment instead of the first segment and why that is a standard in string based problems. In any partition that you create, what can the last segment be? It can either be one element, the last element, or it can be the combination of the last two element, or it can be a substring of length 3 that ends at the last index, and so on. Now, do you know which suffix should you choose as the last element so that the remaining string can be partitioned into maximum number of valid segments? The answer is that you don't. However, one thing that you do know is that the last segment has to be one out of these n possibilities. So there are n possible choices for the last segment. So which one do you choose? You choose the one that gives you the maximum benefit. But how do you define a benefit? A benefit will be that assume that you have selected this segment as the last segment. Then, of course, you need to verify that is this even a valid last segment. That is, you will have to enforce checks to make sure that this segment is a prefix of the original string. Like this part and this part should match. Assume that you have done that. What next? If this is the last segment, then of course this has created one part. But then you would like to know that for the remaining section of the string, for this section, you still need to solve the original problem on it. That is, what is the maximum number of partitions that you can do on this prefix of the string such that each segment is a prefix of the original string. So you can already see the dynamic programming creeping in. If you define dp of I to be max number of partition max number of partitions of the ith prefix, that is of str 0 to I. If you have this dp definition, then you can realize that for computing dp of I, so let's go to the next slide and let's see how we can compute dp of I. Not able to copy it properly, that's fine. So assume you have this very big string of length n and you are only interested in computing dp of I, and this is the index I over here. This is index I. So we already discussed that you will try all possible choices for the last segment of the partition, and that last segment can start at, let's say, index L. So L to I should create a suffix that should be a valid suffix. So it can either be this one, or it can either be this one, or it can either be this one. Now assume it is this suffix that you have chosen as the last segment. Then for the, you wanted the answer of this entire big string, right, which ends at I. And then you said that you will pick this segment as the last segment. So you have already created one segment and now you are interested in the answer of this smaller part, like what is the maximum number of partitions that you can create from this left hand side. That is nothing but dp of whatever this is. So this index is L, so this is nothing but dp of L minus 1. So the answer for dp of I, so transitions are actually very simple. dp of I is equal to 1 plus dp of L minus 1, right? And then you take the max of it. You try all the possible choices for L and then you take the one that gives you the maximum benefit on the left hand side. But provided that you can only take this contribution if str L to I is a prefix. So we already have our first algorithm without much hassle. Now you can see that dp of I, to populate this dp you need the answer for a previous dp, which is dp L minus 1. So if you can ensure that you populate dp from L to R, left to right, then by the time you reach the ith dp, you will already have the answer to the dp L minus 1. So the transitions are actually fast in the sense that sure you have to iterate on the possible choices for the last segment, but this computation, at least you will have this dp L minus 1 available to you. You won't have to do any recursion. So you can do it in an iterative dp fashion. And that's it. That's the first algorithm that correctly solves the problem. So if you are a beginner, this itself might be new to you. So take some time to soak in the algorithm and let me actually write the code for this from scratch. Now, a lot of you might find the code section a bit boring, so feel free to skip to the next section because while writing code, I might write it very slow. So we have to implement yeah, we have to implement this compute for string function, which takes in a string and prints the answer. The answer is the maximum number of partitions that you can do on this string such that each partition is a prefix. So first I find out the length of this string. Okay. Now I define dp of n. Now what do I initialize the dp with? Is it 0? Is it 1? What should the initialization be? So let's initialize it with 0 because we will be populating the dp for all the indices in increasing order. But if you think about it, you can actually initialize it with 1 also, because let's go back to the drawing board. If you have this array and I ask you, tell me how many parts can you split this smaller prefix such that each part is a prefix of the original string. So you can say that one trivial answer is that you don't even split. That gives you one part. And of course, a string is a prefix of itself. So dpi has to be at least 1, right? 1 is the trivial solution. So let's initialize it with 1. So we go here and I initialize it with 1. Now we have to decide the iteration order. So usually when I solve dynamic programming related problem, I don't write the iteration order at the very start. Okay, let's say I'm keeping the for loop empty, and then I want to compute dp of I. And remember that if you are here, you want to compute this, so you will make all possible jumps to the left hand side, so you will choose all possible r. Okay, so what I'll do is, since the IDE is not giving me, yeah, since the IDE is not giving me uh, intelligence, so I'll just add some dummy value, just like you do, like I0, I less than n, I plus plus. This is what I usually do, and then I come back to it and see whether this iteration order is correct, or do I need to do the iteration in a reverse order or in some special order, right? So now we have to compute dp of I. Yeah, and whenever you create a dp matrix, you write down the dp definition. So you say that dp of I denotes the maximum number of partitions of str0 to I, such that each part is a prefix of the original string. This is your dp definition. Each dpi entry has to satisfy this definition. So to compute this dp of I, you will have to iterate over all the values for the starting position of the last segment. So the last segment, suppose it starts at L, right? This is what we are talking about. Like, assume that this segment is L, then, and this starts at L and ends at I. Okay, so for now, yeah, for now, let's say that L is equal to 0, L less than equal to I, L plus plus. Okay, keep in mind that all the entries inside this for loop, right, all the initializers will come back to that. Okay, this L equal to 0 might not be correct, but that is not how I approach TP problems. I just first write down all the transition, not worrying about the corner cases, and then I correct all these loop values. So assume that this is a very big array and you'll never run out of bounds or something. So now you have to check the condition that the string starting from L and ending at I, this has to be a prefix of the original string. So you do, there is a function called str.substr, which can take the starting index as well as the length of the substring that you want to extract. So our starting index is L, and what is our length? So to find the length of a closed interval, you have to do r minus L plus 1. So this is the string, right? If you have never used this substr function, this accepts the starting position and the length, right? So you would do if str.substr, if this suffix is equal to a prefix of the original string. But if it is equal to a prefix of the original string, then it has to be equal to exactly this, right? The prefix that starts at 0 and has length equal to I minus L plus 1, right? If this condition is satisfied, only then you should do the transition. And what are the transition? You want to find out the value of dp of I. So you do dp of I is equal to, now you can see that since you already chose this last segment, you want the answer of how to split optimally the segment that starts right before the lth index. So you need the answer of dp of I is equals to max of dp of I comma 1 plus dp of L minus 1, right? And that's it. That's our dp transition. Now all we have to handle is, are the loop indices correct? So you can see that when you are iterating L, you need access to L minus 1. So of course L cannot be 0. So first of all we'll set L to 1 and then we'll wonder about what is the significance of why L can't be 0. So L can't be 0 because you have already initialized this DP with 1, means you have already considered this scenario where this entire string is a prefix of the original string. So this entire string being one part that we have already accommodated in our DP of n comma 1. So that is why it is completely fine if you want to set L is equal to 1, denoting that there has to be at least two segments for the transition to happen. Now what about this for loop? Like, or are all the variables correct? Like, will any of them lead to out of bound? They should not, but it's better to just start I from 1, because you know that if this, for the first element there can be only one valid partition, so I can just start this entire thing with 1, and this is our algorithm. Now what will the answer be? Remember that we have stored all of these DP values over here, and what does DP of 3 represent? This is the index 3. So DP of 3 represent what is the maximum number of partition of this prefix. So what will DP of the last element represent? DP of n minus 1 would represent the maximum number of this longest prefix. And the longest prefix is nothing but the entire string itself. And that is exactly what the problem asked us to find. So the answer can simply be uh, let's say return dp of n minus 1. So this way we have solved the problem. Now let's talk about the time complexity of this solution. So for the time complexity, you can note that there is one for loop over here, another for loop over here, and then even though it looks O of n square, there is actually a function called str.substr, and the time complexity of this would be O of n. Why? Because a substring can be of length n when you are iterating all the subarrays. So the time complexity becomes O of n into n into n, which is O of n cube, for solving this problem when the string is fixed to a particular value. Now let's look at another version of this problem that appeared in Codeforces Round 1087, which was a diff2 round, and it appeared as problem E, a trivial string problem. So although problem E in a diff2 contest might seem very scary, but the problem that we just discussed was one of the sub problems of this same problem. So this one actually asks us to find something more on top of what we have already computed. It defines f of x. F of x is nothing but f of str is nothing but the maximum number of partitions that you can have for a given string. But you need to compute not just f of str, there are multiple queries that are given to you. So there are multiple queries you can see, and in each query they will give you a left endpoint and a right endpoint, and you need to compute the answer for each substring denoted by this formula. So if you have this, then they are saying that in each query they will give you an L and they will give you an R. So suppose this is the R value over here, and you need to compute f of str, which is maximum partitions of the string that you can create for the substring that gets created that starts at L and ends at any point before R, like all the possible combinations you need to find. Let's go back to our drawing board. So we already know how to solve for a single string. Now the problem wants us to compute the answer for multiple strings. So if this is L and this is R, then they say that compute the answer of str L to L, str L to L plus 1, and so on. Then compute the answer of str L to R, and then print the sum of all of these values. So we already know how to compute for one single string. So let's just do whatever the problem is asking us to do. Okay. So we already know how to compute for one string. In this solve function, we'll simply accept the input params, which is the first entry is n and q. Let's accept them. So I do integer n q, in n q, and then they provide the string as input. So I take the string, and then there are q queries. So for each query they provide L and R. Let's take the input, and I reduce L and R by 1 because we follow 0 based indexing while the problem follows 1 based indexing. And then we need to compute the answer, right? So let's just say answer is 0, and we just compute the string, substring, and then find out the answer using our utility function that we just created. So we say that R is equal to L, R less than, or do something like this, I is equal to L, I less than or equal to R, I plus plus, and then the string substring would be str dot substr that starts at index L and has length would be what, I minus L plus 1, right? This would be the length of the string. And once you have this, then you can compute the answer for this substring. So you can do answer plus equals to solve for what was the name of our function, compute for string. So it would be compute for string, and then we'll pass in this sub and we print the answer over here. Okay, now let's compile this. But before we do that, let's talk about the time complexity. So we have already concluded that the time complexity of this section is O of n, and in each query you are computing a substring, and substring can be as big as O of n. So overall time complexity becomes O of n to the power 4 into q, O of n to the power 4 into q. This is the first time complexity that I mentioned in the description of the problem, right? We will eventually optimize it to O of n log n into q, and then it can further be optimized to O of n into q. So now let's compile this. And I'll do g++ e.cpp. compilation is failing. Okay, my bad, I am in the wrong directory. g++e.cpp, and let's verify on the sample input. Let me copy this sample input from here, and I keep it in a file, let's say in, and then I do ./a.exe in, and then put it to a file called out. So you can see 115.66.314.7, 115.66.314.7, so 314.47. So this looks correct. Okay, so now let's submit this solution. So I'm going to submit this solution even though I know that it will lead to time limit exceeded, because I want to ensure the correctness of our slow solution, right? And this is something that I suggest everyone to do, that even if the solution is not optimal, doesn't mean you have to skip the entire problem, right? Like for example, we saw that this is Codeforces diff to A, and if you are lower rated, you might immediately skip diff to A, but that's not the way to go, because even if you don't solve the diff to A completely, even if you solve some easy version of it, you will still learn something out of it. So let me submit this and verify that this is indeed correct. I go to submit code over here. This is the problem. Let's see. We should at least not get WA. We should get time limit exceeded. Okay. So you see time limit exceeded on test 5, which is good. Means they already have very good test cases. So they must have covered a lot of corner case before test case 5. Means our solution is most likely correct. Now, how do we do the first level of optimization? Let's go back to the drawing board again. So you can see that the solution is O of n to the power 4 into q. And one of this n factor is coming because we are iterating this, we are creating a substring in each query and then computing the answers again and again. If we can somehow avoid this, then it will already shave off a factor of n. Let's see if it's possible to shave off that factor. So you can see that you are computing the answer for this segment. That is what is the maximum partition of this segment. Then you are computing the answer for this segment. Then you are computing the answer for this segment. Then this segment. Then this segment. Notice one thing. All of them are prefixes, right, of the string that starts at L. And now focus your attention on the largest segment, the one that starts at L and ends at R. And let's visualize what our algorithm did in that segment. So this is the biggest string that we can form. You can notice that when we were applying the DP definition, that DP itself used to compute the answer for all the prefix already, right? Because it was not possible to find the answer for this entire segment without figuring out the last partition and then asking the answer for a prefix. So it means that when you did the computation for the largest segment, the one that starts at the L and ends at the largest R, the biggest segment, in that all the DP values that you have already computed, those DP values will not change even for this, right? Because this string or this prefix is nothing but a prefix of the original string which starts at L and ends at R. So this is basically just asking what is the DPI value of this particular index I. So instead of recomputing the answers for each incrementally increasing substrings, we can notice that all of them, they form a prefix. So instead we can compute the answer for a biggest string And in this biggest string, we know that all the DP values, they are actually not useless. They will help you because each DP represents the answer for this prefix, right? And that is how, if you know the answer for this prefix, then you figure out that can you append this last segment and uh, create a new partition. So this already gives us a way to optimize from n to the power 4 to n to the power 3, because we will now run the algorithm only once and then reuse all the DP values. So let's do the implementation for that. So we'll not touch this code, and here instead of returning just the last value of the DP, we will return the entire DP array, because we know that it will be helpful later on, right? And while computing the queries, instead of computing the strings every time, let's just find the answer. So for the entire big string, so we do vector int dp is equal to compute for string, and then that would be str dot sub str starts at l and has length r minus l plus 1, right? Okay, so this actually needs a reference. So let me do string sub is equals to str dot sub str l r minus l plus 1, and then I pass in this reference over here. And now how do we compute the answer for this? So if you already have, let's go back to the drawing board again. This is L, this is R, and you have computed the DP value of all the prefixes of this string. Okay, so you have computed DPL, you have also computed DPL plus 1, you have also computed DPL plus 2, L plus 3, and so on. So the problem was asking you to find the answer for this prefix. So which this will be nothing but DP of whatever index this is. So all we have to do is sum all the DP values in the range L to R. Simple. So we will do long answer is equal to 0, and we do for int I is equal to L, I less than equal to R, I plus plus, and we do answer plus equal to DP of, wait, one second. So this DP, right? DP contains the DP value for all the strings, all the prefixes for the substring that you just created. So the indices might not match, but even if the indices are not matching, you can see that all the entries in the DP, they need to be summed up, right? So that's why you can simply do for integer I is equals to 0, I less than dp dot length, dp dot size, I plus plus, and you do answer plus equals to dp of I. Right, now let's run this code and let's see if this is correct. Okay, so I do g plus plus e dot cpp. So looks like it is correct. Okay, so let's submit this solution. This should also get PLE on test case 5, which is good, but if it gets WA, then that's a problem. So you see that it already passed 5 test cases, so the solution is correct, theoretically correct, might not be optimal. Now, so we have already, let's go back to the drawing board, and you see that we have already discussed two sections of the video. One was O of n to the power 4 and the second was n to the power 3. Now, how do we go one step further and optimize it down to O of n square? To do that, let's identify the bottlenecks that exist in our solution. So let me open the code. And here you can see that we already did whatever optimization we could in the query, right? We are computing the DP just once, not for every substring. So the remaining point of optimization, of course, has to be in this segment only. So that is why in the introduction of the video, I said that we'll only be focusing on just one problem, which is how to solve for a single string. Because all these query and all these query optimization, they are just fancy things that are very specific to the video. The problem setter just added it for the fun of it, but the actual thinking skills is going behind this compute for string function only. You can look at it in isolation, and if you are able to optimize this to the best possible time complexity, then it is not hard at all for you to see that this is how you optimize for each query. So let's focus our attention back to this compute for string function. You will see that one major bottleneck is this O of n comparison, which figures out whether the substring that you choose for the last segment is that a valid prefix or not, because this comparison is O of n. Now, can we do this comparison faster? And the answer is yes. This comparison can actually be done in O of 1 instead of O of n. And that is where the next concept of the video comes in, known as Z algorithm. Now, even if you have never heard about Z algorithm, or if you think that this is some advanced data structure or algorithm that you don't need for your level, then you are wrong, because because this Z algorithm, I will teach you how to use it as a black box. And this is how I usually use it, as a black box only. You don't even worry about even the minute details or even any of the details about the internals of the Z algorithm. Just focus on how to utilize it to solve problems. This will unlock new doors and opportunities for you. Why? Because if you are low rated, then you might automatically skip Codeforces E and problem F, saying that okay, I don't know segment tree, I don't know Z algorithm. Of course, I won't be able to solve this problem. But if you at least know these algorithm even as a black box, that is more than enough to give you confidence to at least read the editorial of problem E or problem F. So what Z algorithm is, it says that if you are given a string, then for each index I, suppose this is the ith index, can you compute the longest prefix of this index? Longest prefix is starting at this index, that is also a prefix of the original string. That is, if these three values, they match the values over here, let's say it is ABC, and here also ABC is written, it means Z of I is equal to 3. But had this been, if this had been D instead, then what is the longest prefix starting at I that matches the prefix of the original string? That is AB, right? So in that case, Z of I would have been 2. And this is all you need to know about the Z algorithm. That is, Z algorithm gives you For each index I, if this is the index I, then it will give you what is the biggest segment that will match this segment over here. And all you have to do is invoke that Z algorithm, invoke that Z algo by providing a string. And in the output, for each index, it will give you its Z value. And take a minute to pause this video and reflect upon what Zi represent. Again, I'll repeat. Zi means if this is the entire string, if this is the big string, then and if you are standing at index I over here, then it means what is the longest prefix that starts from I, like what is the longest substring that starts from I and is still a prefix of the original string. So this segment and this segment should match. So now you can already see that we can compute whether this segment I to j is a, whether this substring I to j is a prefix of the original string. How can we do that? All you have to check if is that the substring I to j, right? If this is a prefix of the original string, then it means the z value of I has to be at a length that either touches j or is greater than it, right? So you just have to check whether z of I, which is the length of the substring, which will also be the prefix. So all you have to check is the index I plus zi, whether j lands on the left side of it or on the right hand side of it. Now focus on this I plus ji again. So I plus z of I represents the last index after which, so this is the last index which matches the prefix, right? So let's go back to the original example that we had. Here you can see, let's compute the z value. Since this is the first time we are discussing the z algorithm, it makes sense to devote some time to figure out the z value of this string. So for this, what is the longest prefix? That is the prefix of the original string as well. So that is 1. Now let me also write this down. This is A, B, A, B, A, 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 B, A, A, B, A, B. Okay. Now, what is the longest prefix that starts at B and is still a prefix of the original string? So this starts at B, this starts at A. So of course the Z value would be 0. Anything that does not start with A, Z value would be 0. We can simply set the Z value of all of these as 0. Now for this, what is the longest substring starting at this index and also a prefix of the original string? So A is 1, but AB is also a valid one. But ABA is also a valid one, right? But AB double A is not a valid one because AB double A is not a prefix. So the Z value of this entry would be 3. What about the Z value of this entry? So A and A is a prefix, so Z value is at least 1. But AA is not a prefix of this original string. So Z value will be only 1. So now, if you know the Z value, can you compare if it is a substring or not? Yes, because all you have to check is whether, so this is I and this is I plus Z of I. So all the any substring that we create that starts at I and ends either at I plus z of I, or before that, this will definitely be a prefix, because this entire big thing is a prefix of this big thing. So if you select a small thing from over here, it will definitely be a prefix of it. So when we were looking for the substring check, all we wanted to know is whether I to j is a substring. So we want to know whether this I to j is a small item in this larger segment that matches. If it is not, then it means that it is not a match. Okay, so it's not a substring. So in this way, this is actually one of the ways to do fast substring comparison, right? Especially if you want to do the comparison with the prefix. So now let's apply the Z algorithm. But how do you even apply the Z algorithm when I am not telling you the internal details of it? So for that, that is where the atcoder library comes in. So if you on YouTube, you can search for the tutorial for how to install atcoder library. So this is the atcoder library, and this provides a function. This gives you a class called this has a strings library, and this strings library has a Z algorithm, which is as simple as it could be. Just accepts a string and as an output gives you the Z value for each indices. And how to use it, you can search for how to install atcoder library. So there is a tutorial by RNC403 on YouTube. So he shows how to install that. Yeah, there is a tutorial. I think there is a video as well. Yeah, there is this video, and there is a one time setup command. So I actually use this to configure this on my local setup. So I have that installed, the at coder library. So all I have to do is I go over here, and to use it, it's simple. You just include the atcoder slash strings, and you add a namespace called atcoder. And here, instead of doing the substring check manually, you figure out the z value, right? But first you have to compute the z value. Okay, so you can do that by simply doing vector int z is equal to z algorithm, and you just provide the str as an input. Okay, now you can see that if the you are computing the answer, see, you are computing the answer for index I, and z of I, suppose this is I plus z of I, right? So you can simply see that z of I, so you can say length is what, z of I, right? Then if this length, the length that is the maximum prefix, this is the maximum prefix. If this is the bigger length and you are hidden somewhere over here, then you will always be a prefix, right? So then you can simply check if length is greater than or equal to your length, which is nothing but I minus L plus 1. If this condition holds, then it means that this substring check always works, right? So just this 2 to 3 lines changes and the optimization is done. Now let's verify whether this is correct or not. Let's compile the code. One second, 3, 6, 10. Let's see if it's correct. I don't see a 10 over here. What is wrong with our code? Let's go back and check again. So we have computed the Z algorithm, that's fine. computed this z value, and if length of this is greater than I minus L plus 1, that should also be correct. dp of I we are updating. I dp of L minus 1. Okay, my bad. So yeah, see here, this is index I. We are actually computing the dp value of index I, and we were trying to figure out the left endpoint, right? This is the left endpoint, and we were saying that this is the last partition that we would create. So to in order to check that the uh, in order to check that this partition is a prefix of the original string, you have to compute the z value of L, right? Not z value of I, because z value of I denotes what is the biggest substring starting at I, that is also a prefix of I, prefix of str, right? So that is why here I have mistakenly added z of I. So I will revert this to z of L. Now let's compile the code again. Yeah, this time it looks correct. Now I just cannot copy, paste, and then submit. So that's why Aryan has already shown you a command that you can use. It's called full expand. Full expand dot auto expand. What is the command? Let me check. Okay. The command is full expand. Full expand a.cpp. So let's see if it works. So I have it installed, but cpp. Okay. So unfortunately, this is not working for me because I do all my development on WSL, and that is where I have installed that full expand command. But right now I am recording the video on Windows, and this bash apparently does not have this full expand installed, so that's why it's not working. So no worries, I'll pause the video and I'll generate the code and I'll submit it. So yes, I was able to generate the code which gets outputted in combine.cpp. I did this from my WSL distro since I do not have that full expand alias set up on my Windows, although it should be easy to set up, I believe. But yeah, this is the final code that I got, and let me now submit it. We go to Codeforces and submit this code with the Z algorithm. Yeah, let's submit in, and let's see whether this TL is. It should not at least give wrong answer. Okay, at least it is now passing test case 5, which is good news. But yeah, by now we can be confident that our solution is correct, although it might not be the best time complexity. Now let's go back to the drawing board and discuss the time complexity of this approach. So you can see that the only optimization that we have done is this q factor will remain from these queries. This n factor will remain from all of these queries. And here there are two for loops now, n, and this is now constant time comparison because we compute this z algorithm, and this z algorithm works in O of n. You don't need to know the internal details. So the overall time complexity becomes O of n square for a single string and n for the query part. So now we have already optimized it to O of n cube into q, right? N square over here for these two for loops and n over here, right? So the time complexity, let me write that down over here. So this is O of n cube into q. Now how do we optimize this even further, right? We would like to do the optimization to O of n square, right? Actually, a slight correction. The time complexity should be O of n square into q already, right? Because we already did the optimization over here. Because see, there are q queries. Let me write that down. Q queries, and in each query, we are calling the method just once, right? There is no O of n thing over here. Okay, we are not calling this function multiple times. So inside each query we can see what all are there, right? So this function itself is now O of n square, right? If you check this function, this just has two for loops, simple, O of n square. So you write q into 1 second, q into n square plus n, which, and naturally n square will dominate. So the time complexity is actually q n square into q, not n cube into q. I might have misspoken earlier. So now how do we optimize this even further? Okay, our time complexity is O of n square into q, right? And we are looking for optimizations. But before we do any kind of optimizations, let's look at what we have to work with, right? The only thing that we can optimize right now is the DP transitions, which is just 3 to 4 lines that you can see over here. So let me copy this part and take it to the drawing board. No, not looking good. Let me do something like this. Capture a part of the screen. 1 second. First, let me delete all of this. Capture this section of the screen. Add it to a new page. Okay, now, great. Let's discuss about this, right? Because this is the only optimization that we can do. Because Z algorithm is optimized, query is optimized. So this part has to move from n square to n log n to n, right? Just these 3 to 4 lines, right? In fact, just 4 lines, because this Z of L you could as well have written over here. So now what I want you to focus on is that now this will be kind of a new idea section. So this is what you are doing right now. This is known as a receiving DP. And I have also created some blogs on my CF step website where I talk about receiving DP versus a distributing DP. So there is also a technique called distributing DP. But before we talk about distributing DP versus receiving DP, I want to cover one point that we discussed at the start of the video. That is, when we created this DP definition, why did we start with the last segment? Why not the first segment? Right? Like, why did we say that the last segment either has to be this or this or this or this? Why was that true? Why didn't we start from first? Now I hope you can realize why that was done, because in all these string problems you can utilize Z algorithm, and Z algorithm works best on prefixes, right? Because it matches this to a prefix. So if you can somehow alter your DP definition such that it computes the answer in increasing order of prefixes, then you will have all the necessary tools available for you to optimize the DP. Hence, this is why this is a very common trend seen in string based problems, that all the DP definitions will always focus on increasing order of prefix, like computing the DP value of increasing order of prefix, and that is why you had to make the choice of the last segment from the end of the array, not from the start of the array. So we have to follow a, if you want to go into known territories, right? Because this was a known territories, because it can be optimized by the algorithm provided you only deal with prefixes and not suffixes. So similarly, right now we are in the receiving DP territory. Although you can still do the optimizations from here, but then it's a bit hard to visualize. But if you can transform it into a distributing DP, then you will have a lot of tools available to you to solve that problem faster. Now let me talk about what I mean by receiving DP and distributing DP. So if you want to compute the answer of each prefix, this prefix and this prefix and this prefix and so on, you can go to each prefix and figure out how to compute DP of I, which is what we are doing, right? In each iteration we are computing DP of I. So you are saying that, okay, I need my answer upfront, give me the value of DP of I, and this is the pattern that most of us are accustomed to, right? From the start of our programming journey, this is the pattern that we have been taught, that you want to fill DPI by looking at other DPI values. But there is also another technique called distributing DP, where you don't focus on instant gratification. That is, you say that, okay, I don't care about populating the DPI values of this. I instead want to focus on which DP values can this particular index I affect. Because right now, if you have this array and this is the ith element, so you can see that this ith element is taking contribution from all the elements to its left. That is why it is receiving the contribution, that is why it is receiving DP. But if I can instead focus on the other way around, that is, given a particular element x, how many subarrays will it contribute to, right? If we can figure out, like, if it contributes to this DP value and this DP value and this DP value, so whatever it contributes, we do the contribution then and there. But when you do the contribution, the DP value of x might not be correct, because it is just providing contribution to new elements on its right hand side. But by the time you reach this element, everyone will have provided contribution to it, and the DP value of this will automatically be correct. So nothing new as such, just a way of rewriting things and looking at it from a different perspective. That is, instead of trying to compute DP of I, you say that, okay, I want to provide contribution to everyone who needs it. So our goal would be that, can we take this O of n square receiving DP solution and transform it to a distributing DP1, right? Can we do that distribution? So to do that distribution, to do that receiving DP, let me start a new page. Yeah. So to do the distributing DP, let's focus on any index. Let's start with this index I. Now, and there are a lot of other indexes as well. Let's say this, 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 this. This will contribute to some elements on its right hand side, right? because if you were at this particular index over here, you would make the choice of the last element as this or this or this, and at some point you will make this choice, the one that starts at I and goes till here, and then you can see that this will contribute to the dp value of this index dpr that is to the right of it. But to how many indices will this ith element contribute? So you can see it will only contribute if the last segment that you create is a prefix, and you already know that I plus z of I is the last index up till which the prefix property holds. So assume that this is I plus z of I. So this means that in this entire segment, right, any index that starts, so any dpi value in this segment, they will receive the contribution from you. So this is a valid partition, right? This is a valid partition in any index of this segment. It means that you make this valid partition and then you will receive the contribution of dp of I minus 1, because this is the maximum number of parts that you can split it over here, and you do plus 1 over here. So this means that for all the indices in this range, you take contribution from dp I minus 1. So you can see that dp I minus 1 provides contribution to all the indices in the range I to I plus zi, right? So we can simply rewrite this receiving dp as distributing dp, and if that doesn't make sense, let me actually write the code, and then maybe it might be easier to reason with. Okay, so instead of saying that we want to take the contribution from all the elements, now we want to provide contribution to feature elements. So this might be actually very new to you, but if you solve some problems on it, I have some practice problem on it that I will add it in the YouTube comment section. You will like, this will become natural to you. Okay, on how to provide contribution to certain indices. So here let me copy paste this block so that we know what we are modifying. Okay, and now we say that we worry about, think how many, think which indices dp of I minus 1 or I can affect, right? Or basically, if partition or something like, if last partition is done starting at index I, then the string that can be formed would be what? Str I to j, right? And j has to be less than or equal to I plus zi, right? Only then it will be a valid string. Okay, so you can simply say that for int j is equal to I, j less than I plus zi, j plus plus, then you say dp of j is equals to max of dp of j comma dp of I minus 1 plus 1. This is the contribution that I minus 1 is providing to all the future elements, right? Now whether here should it be less than or should it be less than or equal to, let's think about that. Okay, now let's go back to the drawing board. Here you are doing the partitioning like so. You have element I over here. Okay, and think about if So see, whenever you encounter a scenario where you need to figure out whether you need to add an equal to sign or not, you think about when z of I is equal to 0. If z of I is equal to 0, it means that there is no valid substring. If there is no valid substring, can there be a valid partition? No. So if there cannot be a valid partition, it means that the condition will become z of I is equals to I, j less than I, right? So if z of I is equals to 0, you don't actually want to do the contribution. So that's why this should be less than and not less than or equal to. So this is just a rewrite. This is just a rewrite of the original receiving DP. So here you see you are taking contribution from older element, but here you are providing contribution to newer elements to your right. And what are those newer elements? So you can see that these newer elements are nothing but, so if this is index I and this is index I plus zi, right? So any prefix that you create starting from here, this will always be a prefix of this. So that is why dp I minus 1, the maximum answer of this contributes to these elements in this range. Okay, so this is our distributing dp. Okay, so now let's submit this code and verify that this distributing dp idea is also correct or not. Okay, so to do that, you know that I have this string one, but since my expander is not working, there is also another way which you can do. Like I already have the code that I submitted once, so I will just replace my functions over here, like this one, compute for string, and then I copy this over here and then replace this over here. Okay, and now let me compile the code. G plus plus. Okay, looks correct. Now let's submit it. So we are not changing the time complexity as such, you'll realize. We are just rewriting things in a distributing DP manner. Why we are doing that? That will become clear in a while. But let's see if that's okay. So this is actually correct. And for some reason it actually passed one more test case, which is good. But yeah, time complexity is still the same. So there is no optimization that we have done. But now it will make the problem somewhat easier to reason about and somewhat easier to think. Okay. So how do we optimize it down even further, right? Right now the complexity is what? O of n square into q, right? And we want to optimize it to O of n log n into q. So let's go back to the code. Okay, by the way, okay, apparently I didn't delete the old code from here. I should. Okay, this is the simple code, just these 3 lines. Okay, we are looking to optimize just these 3 lines using any data structures that is available to you. How can we do this optimization? Let me, yeah, let me take this to the drawing board. Okay, Control C. So now you will see that this has a general form that for any index I or I minus 1, yeah, for any index I or I minus 1, you are providing the contribution to all the indices j which start at I and end at I plus ji. So this is I, and let's say this is some value right endpoint, like let's say j, right? So you are doing contribution in a range, right? You are increasing all the dp values, you are updating all the dp values in a fixed range, right? Previously that was not possible. In receiving dp, for one element you are taking the contribution from multiple elements, so it was not clear what was going on. But now that we transformed it into a distributing dp, you can see that one element distributes to a contiguous range, right? And that range is I to I plus ji. So now you need a data structure that can efficiently do something known as chmax. Okay, I don't know what that actually means, but apparently this is what the chmax dp is. Whenever you see the format of you want to do in a range L to R, you want to do set ai to max of whatever ai is, comma, a constant k. So here you will see that in the range I to I plus ji, which is a contiguous range, you want to set each element to max of what it already is, comma, a constant. Why is this a constant? Because you are iterating from left to right and you know the dp value of dp I minus 1. So you need a data structure that can efficiently perform chmax dp, okay, which can essentially do range updates, and the range updates should look like this: ai is equals to max of ai comma k. So luckily for us, a data structure for chmax dp already exists, and that is known as segment tree. In fact, that is the lazy segment tree. And again, I'll not dive into the internal details of the segment tree because Coder has already abstracted out everything that you need to excel in competitive programming. You just have to understand how to use those signatures and functions that they have provided. So this part is actually, this chmax dp is actually very standard on how to do via lazy segment tree. So I will skip this part. I will just show you the code on how I can simply take my function over here. I can simply take my code over here. I can plug in at Coder's lazy segment tree that provides chmax dp, and chmax dp is nothing but getting a data structure that can do a range max updates with a constant value. And the lazy segment tree that at Coder provides, that is capable of doing that. Okay, so the next time you come across any problem that updates the dp value in a range in this fashion, ai is equals to max of ai comma k, you can refer back to this video and the segment tree library from Coder. And that was also one of the main goals for creating this video, so that you have some reusable templates the next time you encounter chmax dp problems. Okay, now, so using that is simple. I'll show you how. I also have some videos on my channel that I link in the YouTube channel, but those videos talk about how to use segment tree from Codeforces, not the lazy segment tree. Okay, for lazy segment, I do have one practice problem that I can refer you to. But yeah, coming back to the topic. So to use the lazy segment tree, all you have to do is include the lazy segment tree at coder slash lazy seg tree, and then you have to define certain ops, mappings, and composition. That part we can do by simply going over here, looking at their samples. Like let's say this is the lazy segment tree sample, and they say that you have to define some. Let's look at an example. They define some op, e, mapping, id, and s and f, right? So you can just do something like using s is equal to int, because we are only dealing with integer, and f is equal to int, right? Because those are the only data structures that we are dealing with. So s and f we have defined, and the op will be how do you take this a and l and r, and what do you want to return, right? So we want to return maximum, so you can simply do s op, and it would be s l s r, and you can simply return max of l comma r. Okay. Now the second thing that they want you to do is implement something called E, right? So E would be, let's say the minimum value, you can set it to 0. So E you can simply return 0. Okay. Next thing that they want you to implement is a mapping. Okay. So what is this mapping? So I'll not dive deep into what mapping is and etc. But I can, so at least from here I can assure you that segment tree, so the lazy segment tree is capable of doing the Chmax range updates if you just make the composition and the mapping as max. Okay, why that works is a different story. That works because it follows the properties of the monoid, but you don't have to worry about that. Okay, next time you encounter anything that wants to increment something in a range by doing x is equals to max of x comma some constant, you can use this template. Okay, and there are other uses of lazy segment tree as well. But okay, even if you don't want to understand the lazy segment tree part, that's fine. At least the next section that we'll cover, right, that will have no reference to segment tree, and that should be easy to understand. Okay, so here also mapping will also keep max. Everywhere we want to keep max. Okay, so mapping we have defined. Then we need composition, so we do composition, and for composition we need FL and FR. So we do FL, FR, and here also we just do return max of L comma R. Okay, and then finally we need ID. Here we return 0. So essentially what we have done is, so they need two things, right? Op and E, and composition and ID, as well as the mapping. Sorry, mapping, ID, and this, right? So here you see that we have just taken max and 0, and here also everywhere max and then 0. And then to use it, you just have to initialize the segment tree and call the updates query on it. Okay, so before, when you want to do this range ch max updates, you create the lazy segment tree like so. You do lazy segment tree, and you have to provide your data structure s op e f mapping, one second, mapping, composition. This is the standard format to initialize the segment tree. You initialize the segment tree of length n, and then yeah, now you want to distribute the contribution. Okay, how do you want to distribute? Left endpoint is I. Okay, so let me set it. Integer left endpoint is I, and the right endpoint is the minimum of n minus 1 comma I plus length minus 1, right? Because we saw that we should not be touching I plus length, right? Let me set the length as z of I. Okay, and then all you have to do to apply this range update, like convert this for loop into a single one, is simply do segment dot apply L comma R plus 1, and then whatever you want to update with dp I minus 1 plus 1. Okay, now one quirk that you will notice is that every time you want to do an increment in a particular range of segment tree, you always have to use L comma R plus 1, not L comma R. This might seem very counterintuitive to you, because why are you using so instead of using closed comma closed range, at coder libraries in all places they use closed comma open, means the last entry that you provide should not be touched. Okay, so they are asking you the last entry that should not be touched, and we want the last entry that should be touched is the rth entry. So that is why we provide R plus 1. So this might seem very counterintuitive, but this is actually the norm in the industry, and you might have actually used it in the past. Because think about when you use any data structure from the standard library, like lower bound. Okay, when you do lower bound, do you say a dot begin comma a dot end minus 1, or do you just say a dot end? You say a dot end. Why? Because you want the library to not access the last iterator that you gave. So at Coder follows the same philosophy and it does not touch your last entry. So that is why you provide r comma r plus 1. Okay, so you have applied this range updates for this, and then you compute the dp value, like you extract the value because you are going from left to right. So after all the, see, when you receive the ith when you reach the ith element, all the updates will already be applied on this ith element. So you extract the contribution out from the segment tree. So you can simply do max of dpi comma segment dot get the value of I. Okay, and that's it. Let's compile the code and check. And you can see that we are getting the correct output. Okay, now to submit again, I'll have to do the full expand. So I'll not submit it. I know that this is correct since I've already implemented it before, but I hope the idea is clear, right? We started with that receiving dp, then we migrated to the contributing dp. Why was the migration done? Because that is the known territory. Because if, because that can lead you to the chmax optimizations that exist. Because if one index is providing an update to a contiguous range, then this updates can be efficiently handled by the encoder's lazy segment tree. That is what we have done over here. Now the time complexity of course becomes O of n log n into q, right? Because now this is O of n, the algorithm, and this is O of log n per loop iteration. So overall O of n log n. So now you see that we started with O of n to the power 4, right? Then we went to O of n to the power 3, then to O of n square receiving dp, then to O of n square distributing dp, then to O of n log n using chmax range updates via lazy segment tree. However, even if you did not understand a thing about chmax range updates dp, this chmax dp can also be solved. The general version of the chmax dp can also be solved using something known as a heap sweep. So that is the last part of the video that we will discuss, where we'll talk about the heap sweep algorithm and why you actually don't need a lazy segment tree to do chmax range updates. So let's see. One second. Yeah. Now we want to talk about heap sweep. So the idea behind heap sweep is this. You want to do optimizations for problems where one index, this is an index I, this index provides contribution to this particular range on its right hand side. If you want to optimize this kind of dp, this kind of distributing dp, then instead of using lazy segment tree, there is a very neat way to do it via simply heaps. And the way to do that is, you say that when you are iterating from left to right, right? And suppose that this is index I, and this will provide contribution to L to R. So we do the contribution in a lazy order. That is, we say that, okay, instead of iterating the entire range and then providing the contribution that will already be O of n, let's record how much contribution do you want to provide to me at this position. So at this index L, we will maintain how much contribution, we will maintain the interval for the contribution. That is, this ith element provides contribution from L to R. So at each index L, we will maintain the value, like how much dpi you want to contribute, comma R. So this element is providing some contribution to this range starting from L. Now there can be some other element over here this might also provide the different contribution to the same range. So we'll record that, and this range might not necessarily be this, right? It can start at this L, but it can end at, let's say, here. It can be this range. So it can be val comma r1, val comma val2 comma r2, and so on. So what we do is, every time we encounter an element, instead of distributing the contribution right away, we look at the starting index of the contribution, which is the L, and there we keep track of all the intervals that it should cover along with the values that it will provide the contribution to. Okay, so this is how each element will lazily propagates its information forward. Okay, so you can see that once you have crossed this red element, you are not losing anything, because you have recorded that at this point everything will get contribution equal to val2 comma r2, which means that all the elements in this range must be set to max of x, must be set to max of x comma val2. Okay, similarly, when you cross this element, you are not losing anything, because all the elements of this range should be updated to val1 comma r1, right? So the only thing that is remaining is, now you have, so now you will have for each index I, they will maintain a list of the intervals that they will be contributing to, right? The contribution will start from these indices. So when you go from left to right, okay, you can store all the valid contributions. So all the contributions that you are getting, you can store all of them in a heap, because you only care about the maximum valued contribution. So you store all these val comma ri, you sort them in order of val, right? So you say val highest, and then you do val lowest, right? And then when you reach a particular element I, all the elements that are over here, right, they will provide contribution to it, provided that their right endpoint crosses I. So what you can do is, you can check the highest valued element that exists over there, because this is the one that can provide the maximum contribution. But if this highest valued element cannot provide contribution to I, and when can that be? When RH, which is the right endpoint for this highest valued element, if this RH is less than I, it means it cannot provide contribution to I. But notice that it also means that it cannot provide any contribution to the future elements on the right, because if it is not capable to reach over here, then of course it will not be capable of reaching on the right hand side. So that is why you can completely remove it from the heap altogether. Then you check the next highest element. If it can provide contribution, great. Take the contribution and no need to look further down the heap. Why? Because this is a max heap. You are already taking the contribution from the best possible element that you can get. But if that element is expired, that is, its right endpoint is less than I, then you cannot get any contribution from it. So that's why you can simply discard it from the heap. So in this manner, every time for each index, you are just adding some interval, adding exactly one interval at the at the dp of L, or whatever range that you are maintaining. You are inserting, you are doing a pushback for the contribution that it provides along with the right endpoints, and then when you are iterating from left to right, you are keeping all the intervals in a max heap. Okay, and for getting the actual value of dp of I, you are saying how many elements provide contribution to it. So all the contribution for I must come from the left hand side. Okay, all the contribution from must come from the left hand side. This means that all the active elements in the heap will contribute to it. But why do we need to look at all the active element? We can only look at the best element, which is the topmost element of the heap. If that element is not expired, meaning if it can provide this contribution where L is here and R is here, we take that contribution and we move on, right? And then we keep repeating this process until we encounter the topmost element to be expired, that is R becomes less than I. So then we remove it from that max heap, and then we look at the smaller valued elements. So this is another technique called heap sweep, using which you can solve any Chmax range updates DP problems that you see over here, right? Because this can solve a general Chmax. Note that this has no connection to the string problem that we just discussed, right? This is for general Chmax range updates. So let's look at the implementation. I know this might be a bit confusing, but this is a bit of new concept, so maybe spend some time on it, and eventually it might become clear. Try to do some like dry runs, and yeah, eventually the idea will come to you. So let's implement the final section of the video before we talk about one more optimization that can do it to O of n. Okay. So we'll keep this section as it is. Now let's start with okay, we'll delete segment tree later. So here for each index we discussed that, yeah, for each index we have discussed that this is element I, and element I, this is index L, and this is index R, and this is the end of array. So I will provide contribution to all the elements in the range L to R. So we said that at the location of L, we'll push back the contribution, we'll store the contribution as an interval. Okay. So we do something like you will have to maintain vector of so that will be, for each index you will have to maintain a vector, because there can be multiple entries, right? So that will be vector of pair int, and then we can say it will contribute till. So we create a vector of length L, of length n, which will store all these. For each L, it will store the dp comma r value, right? So let's say that it stores val comma r. Okay. And then you also need a max heap. So for that you can do max heap via priority queue, and max heap should be by the value and not by the index, right? So you need a max heap, and you can say that heap stores val comma r. Okay, all the active intervals, all the active intervals. Okay, now you start sweeping. So you start sweeping from left to right. Okay, and then again, just like before, just like before we computed length L and R. So we do the same thing. We compute length, we'll compute L. So dp I minus 1 will start contributing from I to I plus di, right? So we said that I'll just copy paste, okay? So that you know that I'm doing the same thing, nothing fancy over here. So I'll just copy paste over here. Okay. Then we want to contribute from L to R. So at the index of L, we'll push back. We'll push back dp of I minus 1 plus 1 comma R, right? We pushed it. Okay. So now this index I, right? This index I that we have drawn, it has provided its contribution, right? Now it is time for it to receive its contribution, right? But before it can receive its contribution, there you can see that it will have some it will have some val comma r stored inside of it, right? Inside this I. So these are the intervals that has not been activated yet, but now since we are at element I, we should now activate this interval. Okay, so we will activate this interval by, so all the values that are already and at the location will contribute till I. View, activate it. How do you activate it? By simply pushing it in the max heap. And now finally, for the showdown, it's time for AI, for the DPI to get its final value, right? Because we are crossing from left to right. Okay, we are crossing from left to right. So once we leave AI, there is no way to compute this DP value, right? So now is the time where everything is activated. All the intervals that are contributing to this ith element, they have been activated. So now you need to compute the maximum value of the DP. And how can you do that? All you have to do is look into the heap, right? And look into the best value in the heap. And if it has expired, just discard it, because if it is not able to help DP of I, it will not be able to help any of the elements on the right hand side. So right now we'll add a comment like what it is doing. This is activating the intervals. Activating the interval. And then we want to remove the expired intervals, right? Removing the expired intervals. So how can you do that? You say while not heap.empty and heap.top dot second. Basically the r value is on the second one. If this has expired, meaning if the contribution has ended before I, it means that it cannot provide any help to the future element as well. In fact, this is the property that makes heap sweep work, right? Because if you cannot help I, you cannot help any of the elements to the right hand side, because your contribution was to a contiguous range, right? So you just simply pop the heap. And then finally, if the heap is not empty, you take your contribution from there, because now all the elements that are inside the heap, they are from the active intervals. So you can actually take the contribution from there. So dp of I will simply be max of dp of I comma heap dot top dot first, because the first value is what we had stored, right? We don't need to add +1 or anything over here, because we already added this +1 while pushing to the dp value, right? And that's just it. So you can see this is problem E, right, from Codeforces Round. But the solution is so simple. But it is only simple if it is just 5 to 6 lines of code, right? Not more than that. No segmentary, no nothing fancy, right? I can even delete all the segmentary logic from here. I can even remove the imports for segmentary. Let's remove the import from segmentary. Okay, and you see just 5 to 6 lines of code, and this heap sweep technique can solve the general range max chmax dp updates. Let's compile the code and see if it works. So 15,314, let's see, 15,314, 15,314, yeah, it should work. Yeah, it is giving the correct result. So now let me submit this, but to submit it, of course I will have to replace it from over here. I can do that by Right. Okay, let me copy this, submit. Hmm. Okay, this actually ran till test case 8, which is good. Why the difference? Because segment tree, of course, it has higher constant factor, so that's why implementing by simple heaps led us to crossing one more test case. And now we have solved the problem in time complexity O of n log n into q, right? Without using segment tree, using heap sweep. And that's the end of the video. But you will see that I did not get an AC on this problem because apparently problem setters want an O of n into q solution. Okay. So even though I have not yet implemented the O of n solution myself, I have an idea of like what's going on there. I'm just not motivated enough to do that because see all the other concepts that I discussed, right? Like Chmax, range updates, DP via lazy secretary or via heap sweep, or the Z algorithm, or the receiving DP, contributing DP, or the initial DP definition, etc. that we created. All of them you can reuse them in the future. But this optimization from n log n to O of n only works because of the setting of the problem. There is a special property in this problem that will help you to get rid of the heap in the heap sweep and replace it with a stack. And what is that property? So that property is when you define your DPI value, and in fact, I won't say that you can't reuse it. I have seen that idea in a lot of string based problem. It's a very cool idea. So the idea is when you define a DP on a string, okay, when you define a DP on a string, then you have defined that dp of I is the answer for this prefix and dp of I plus 1 is the answer for this prefix. So can you find the relation between dp of I and dp of I plus 1? So you will realize that dp of I will always be less than or equal to dp of I plus 1. Like it will always be, so it will always be in this fashion, like it will always be in increasing fashion or it will remain same. Why? uh, because if you have a partition of this string, if you have like if this is I, if you have a partition, then the last element, it is either a prefix, like it is either equal to the first character over here, and then if this is indeed equal to the first character, then you have a new partition, right? So in that case dp of I plus 1 is equal to dp of I plus 1. But if it is not a prefix, then it has to be merged into this segment over here. It means that you have to split, right? You have to split your a partition even smaller, right? So it means that if you had 10 partitions earlier, now you can only have 9 or 8 or 7 or something like that, right? You cannot have more than 10, because if you had more than 10, it means that even if A was not there, you could have made more partitions over there. So this monotone property of dp of I plus 1, and with this you can see that you start with dp of I, so you start with dp of I is equal to 1, and you can see that every time it can only increase by 1, right? Because you either start a new partition over here, or you become part of an older partition, in which case you will have to make some compromises and reduce the number of partitions. So that's why dp increases very slowly, like it can only increase by 1, right? It can only increase by 1, but when nothing is working, it can ultimately even fall down to 1, and then it can only increase. Then nothing is working, it can even fall down to 1, then nothing, and then it will increase. So this is the monotone property. So then you can see, so this monotone property that whenever you see a DP that only increases, or maybe even if it falls down, then only increases very, very slowly, like only increases by 1, then you can optimize it by sets. So I have some ideas about it, but yeah, I think you can read the editorial for that. I'll not comment more on that. But this is actually a very common idea. In fact, if you look at the longest increasing subsequence problem, LIS problem, that also uses the similar idea of something that increases very slowly, or this monotone property. Okay, and in fact, in strings problem, it is a very common recurring theme, like something. In a string problem, like most of the time whenever you define DP, right, there are only n length, right? So most DPs, they are usually on lengths, so they increase very slowly. So this monotone property is what will lead you to the optimization that can help you move from heaps to stacks. But do I believe that it will be applicable to a feature problem? Sure, but it's very unlikely that I'll attempt that feature problem, at least now, in the contest. So that's why I'm not creating that video. And I think even if you solve till O of n log n, that's good enough, right? Because even if you don't solve, like I said, even if you don't solve the entire problem, you should solve at least some sub problem that you can reuse in future, right? I taught you a lot of things in this video, like how to use segment tree, that you can go and like also read Aryan's blog on how to set up segment tree. And then I have some practice problem on how to use segment tree. Then we looked at the algorithm, heap sweep, receiving DP, contributing DP, and the optimization of prefix sum, right? That we did in the query part. So yeah, all of these we covered. And yeah, I know that this was a very long video, and I might have repeated a lot of things because it's kind of difficult to get feedback when you are recording such a long video. But I hope you still were able to get the benefits out of it by skipping to certain parts of the video, or maybe speeding up the video. So yes, I was experimenting with a new format on my channel by adding this type of video where we just go with the flow. And see, the alternative is that I don't upload the video, right? Because if I have to like prepare something and then think about what to say, then that of course takes time and commitment. So I can't be that regular. But if it's just a video where I'm just talking, and even if that leads to duplication, right, like I might be repeating the same things over and over again. But if you think that it will help you, then you should yeah, definitely let me know in the comment section, and I'll try to add more more videos of this pattern. Thank you.